Good morning, students. Today we are going to see about the third unit, crystal structure. What is meant by crystal? As before earlier, we studied in our school days, I think I studied in school days, what is meant by matter. We have three different types of matter, okay? That is solid, liquid and gases that we are all studying. And the fourth matter is the plasma. Okay. Now we are going to see about the solid structures that is called as a crystal structure. Okay. So why we are to study about the solids? Why its structure we have to study? Okay. See, material. What is the material? A material is composed of atoms and molecules. Any material that is composed of atoms and molecules. Okay. All these matters are held together to form a force of attraction. These atoms and molecules have a force of attraction and repulsion forces will be there. Okay, so this our force of attraction is called as bonds. Okay. We have many type of solid materials that is called brittle material, ductile material. These are the properties of solids. Brittle, sometimes it behaves as a ductile, sometimes it behaves as a malleable, and sometimes it is very strong, sometimes it is very weak. These are all the general properties of a solid material. Okay, so we know about the matter, solid, liquid and gases. And why we have to study about the crystal structure is, that is the solid structure is, we know materials. The materials is composed of atoms and molecules, and all these are being bonded together with the force of attraction. Generally, these solid materials have the properties like brittle, ductile. Brittle means it will be breakable, and ductile. Ductile is also a type of breakable, but different categories. Malleable, strong, weak. It is sometimes it behaves as a bad conductors. Sometimes it behaves as a good conductors. And some materials have a magnetic property, and some materials will not have a non-magnetic properties. So classification of solids. According to the internal atomic structure, these solids can be classified into two different types. One is crystalline and another one is non-crystalline. Sometimes it is named as amorphous materials. What about crystalline solids have an ordinary arrangement of atoms. But in amorphous, it is irregular arrangement of atoms. That's the main difference between the crystal material and amorphous material. The solids have a regularly arrangement of atoms. So what its force of attraction is very high when compared to the amorphous material. Since amorphous material is an irregular arrangement of atoms, it has an weak repulsive attractive force between the solid material, between the atoms and molecules. And these crystalline solids have definite geometry. Since it is a regular arrangement, we can mention it's about shape. But amorphous, we cannot able to name the shape of the material. Okay. In crystalline materials, these have a long order of arrangement of particles. But here it is short range order of arrangement of atoms. Okay. Since for regular arrangements, crystalline solids are regular in arrangement, it is also named as an anisotropic in nature. That is same physical, that is different directionality. So we are naming it as an anisotropic, different directionality. When you are coming to the amorphous material, it is an isotropic in nature. Isotropic, we cannot define the direction. Then these examples for these crystalline materials or true solids are quartz and sodium chloride, etc. Example for the amorphous materials are glass, rubber, etc. Now we can see about the basic definitions in crystallography. First one is crystal structure. This is nothing but a arrangement and the disposition of atoms within a crystal. What about the studying of these arrangements is called as a crystallography. In what way we can study these arrangements of crystals? By using X-rays, electron beams and neutron beams, we can study about the crystal structure. And studying of crystal structure is called as crystallography. Okay, so before coming its structure, the base is called as lattice points. It denotes that portion of the atoms or molecules in the crystal. So in which, what are all the points we have to connect to give a structure is called as a lattice points. And since we are drawing these points or atoms arrangements in space, that is in three directions, coordinates x, y and z axis, this is called as space lattice. Okay, three-dimensional array or collection of points, how these atoms are arranged is called as a space lattice. Simply we can say it is a geometrical representation of the crystal structure in terms of lattice points. Okay, so this space lattice plus basis will give you the crystal lattice, and this is called as when these lattice points are repeatedly arrangement to form a structure, it is called as a basis. Basis in space lattice is called as a crystal lattice. And some basic definitions in crystallographic structure, we can say unit cell, that is these arrangements forms a structure. The simple one base is called as unit cell. The unit cell is the smallest volume of a solid or a geometric figure which gives the entire crystal is built up by the translation repetition in the three direction. Okay. We can say this in space lattice if we draw this unit cell, and the intercepts are called as A, B, C or called as primitives. First crystal structure we can see about the base body centered cubic. From the body centered cubic we can see a unit cell which consists of 6 atoms, that is called 8 atoms at the corners. But it is not fully shared in the respective unit cell. It is shared by the nearby unit cell. So one atom, that is one unit cell which consists of 8 corner atoms, but it is shared by nearby unit cells at the top, bottom, right, left and the front and back. So all these are shared, then it is called as 1 by 8 into 8. So we have only one number of atoms in the corner. And since it is a body centered cubic, in diagonally at the center of the unit cell we have one atom which is touching with the diagonally, it is touched with the corner of the atoms. Okay. So we have 1 plus 1 corner atoms, totally we have 1, and the body diagonal is 1. So we have number of atoms is 2. We have crystal structures as simple cubic, body centered cubic, face centered, hexagonal, diamond cubic. All these are different types of structures. Now we are going to calculate the packing fraction of a body centered cubic and face centered cubic. So we have number of atoms as 2. The nearest neighbor of a corner atom or body centered atoms are not other corner atoms. Now we have to calculate the neighborhood atoms. If we consider the corner atoms, all it is shared by the nearby unit cells. So we cannot say it is a neighborhood atom. Only the atoms which is touching with the body diagonal atoms, it is called a nearby atom. So we have 2 atoms shared which is attached with the body diagonal atoms. Since there are 8 surrounding unit cells for any corner atom, their body centered 8 atoms from the nearest neighbor for any carbon atom. So the number of atoms in the unit cell we can calculate this. So calculation of density of packing fraction. So the center one is called as a body diagonal and called as with this body diagonal atom. These two are the neighborhood atoms for this body diagonal atom. If we calculate the density of packing fraction, first we need the number of atoms is 2 and the neighborhood atoms. From this neighborhood atoms we can able to calculate the atomic radius of the atom. So atomic radius is given by the distance E, which is center one is 2r and the left right is r plus r. So we have totally 4r. So the radius r will be equal to root 3 divided by radius. Since it is body diagonally arranged, its value is root 3a. So 4r equal to root 3a, and we can say this r will be equal to. Then coming to the packing fraction, the formula is V divided by capital V. That is B is nothing but number of atoms in the volumes occupied in the unit cell and divided by volume of the unit cell. So number of atoms is 2 that we already calculated into the volume occupied by the atoms is 4 by 3 pi r cube divided by total volume of the unit cell. Since it's a cube, we can say it is a cube. So we have calculated this as 8 pi, that is volume occupied is 4 by 3 pi r cube. We know that r equal to root 3 by 4a. So if we use this formula and we calculate this, the packing fraction is about 68% of body centered cubic. For simple cubic, we have only 52%, and for body centered cubic we have a 68%. When compared to the simple cubic, body centered is a densely packed. Thank you, students. In next class, we can see about the face centered cubic and hexagonal closely packed structure, and we can calculate the packing fraction for these structures.